So I'll present our last research about iodine reactions and their effect on perovskite cells degradation. You see my screen and everything is fine, right?
Everything perfect.
Okay, so I'll start with a brief slide on the research process with simulations and how it differs from experimental research. Later, I will talk about previous studies we did on perovskite solar cells and the conclusion that emerged from them. And for most of the presentation, I will focus on our latest research, which deal with the effect of iodine on perovskite solar cells. And I'll skip the perovskite introduction. I believe you are familiar with this material, so I'll jump right into the subject. Okay, so my research is based on simulations. And I'll start by clarifying what simulations mean and what the research process includes. So there really isn't a big difference between the stages of experimental research and the stages of simulation-based research. After we made hypotheses that we wanted to test, so instead of producing a device in the lab, we build a device in a simulation tool. We use TCAD and Taurus. And the next step is different from experiment, as we need to tell TCAD which materials we use. We need to add the basic material parameters, such as energy levels, mobility, and the electric constant. And we also need to tell it how electrons, holes, and in our case also ions, behave in the device. So for this, we choose the physical models that describe the transport, recombination, reactions, etc. Once the device is ready, we run the simulation. The output of the simulation are datasheets and graphs. And the last step is analyzing the results and concluding, and the same as in experimental research. So this is a very concise explanation. I can make a whole presentation just about simulations. So I will gladly answer any questions about simulations at the end of the presentation. Okay, so now we can start talking about perovskite solar cells. You probably know that the main problem of perovskite solar cells is their poor stability. Perovskites suffer from extrinsic instabilities due to oxygen and moisture, as well as intrinsic instabilities, which leads to a decrease in their efficiency in much less than a year. So, for example, yeah, I'm sorry, I wanted to do that. For example, here we can see the front and back sides of a fresh perovskite solar cell. And here the front and back of aged perovskite solar cell, which is encapsulated and kept in a nitrogen environment. So this device deteriorated, although it wasn't exposed to environmental conditions. And many studies deal with the perovskite parameters and how they affect their efficiency. So, for example, in our previous study, we showed the effect of the perovskite grain size on the solar cell efficiency. So here we can see an AFM image, and the PCE and the VOC of each grain contributes relative to the values of the all layers, which are marks in these lines. The small grains functions as recombination hotspots, so we would like to avoid them entirely. The conduction in the perovskite is ionic-electronic conduction. The ions, which detached from the crystal, take part in the currents and change the charge distribution in the device. And they also can affect the electrical measurements and cause hysteresis, but worst, they cause internal deterioration of the device. So we found it important to explore them. In another previous work, we show the simple connection between the thickness of the blocking layers to the solar cell stability. So the ions reaching the metal electrodes can react with them and degrade the device. So it is necessary to prevent their arrival to the electrodes. So here we can see that the color of the device and the metal uniformity are preserved better with a thicker blocking layer. And our graph shows the ion density near the contacts as a function of time for different thicknesses of blocking layers. So we can conclude that the motion of ions within the blocking layers is important enough to study. And the thicker the layer, the better blocking, ion blocking we get. But although the electronic blocking organic layers can delay the ions, they don't block them entirely. In another previous work, we pointed out the relation between the ion concentration near the contacts to the energy barriers between the electrodes to the blocking layers. So with the right choice of electrodes, we could get less ion accumulation near them and probably also better stability. Okay, so that's all with the previous work. From here, I'll talk about the main subject, the iodine reaction effect. So quite a few studies discuss the presence of free iodide anions in the perovskite. The iodide's formation has low activation energy and non-neglectable diffusion coefficient. And under external energy, such as illumination or heat, the density of free ions in the device increases. But at the same time, only few works discuss the reactions in which the iodides take part. We know that the iodine anions can react with holes and become neutral atoms. The iodine atom is a halogen, so it is prone to react with an electron and return to be a negative ion, or react with other iodines and become a molecule. So eventually, we will have several iodine species inside the perovskite solar cell. And the iodine can react with other iodines or electrons and create different elements. So this is the energy graph of the different reactions. It was measured in a solution media, but it gives us some idea about the energies compared to the conduction and valence band of the perovskite. We can see it here. So it can be seen that most of the reactions have energies that are within the energy band of the perovskite. So such reactions create traps for charge carriers and cause generation and recombination. Okay, so let me demonstrate the recombination process caused by the reactions. So two electrons from the conduction band can react with I2 molecule, thus becoming two anions. The anion can react with hole from the valence band and become a neutral atom. The neutral atom can react with an electron from the valence band and return to be an anion, or react with electron from the conduction band in the same way. The contacts also play part in the reactions if the ions reach them. So this process increases the charge carrier recombination and reduces the solar cell efficiency. And in our study, we show the effect of the above reactions on the electrical efficiency of the device. We did that with TCAD simulation tool, and the reactions we considered in the simulation can be described as a circular process, which includes the following reactions. So we have iodide anion that can react with a hole and become neutral atom. A neutral atom can react with electron from the valence or conduction band and become anion again. Two atoms can react and become I2 molecule, and I2 molecule can react with two electrons and become two anions. So we chose a minimal set of iodine species that can describe this reaction cycle. Okay, so let's go back to the simulations. So the simulation solved the continuity equation of the 5 elements. So we have electrons, holes, iodine atoms, iodine anions, and iodine molecules. But I believe I don't need to elaborate on it. The exchange of the charge and iodine atoms between the elements must sustain the charge and matter conservation equations. And another important equation for the electrochemistry in the device is the reaction rates. So the rates of the forward and reversed reactions depend on the density of the elements participating in the reaction. But also, we can see it here, but also on the reaction constant K. But unfortunately, there is not enough information about the reaction constant K of the iodine species in the perovskite. So to give an estimation for the reaction rates, we use the formula that assumes diffusion-limited reaction. The full formula is not very important, so I won't dwell on it. But I will note that there are 2 main factors in the reaction between 2 elements A and B. The first one is the speed at which the elements reach each other. And the second is the speed at which the reaction between them occurs after the 2 elements come into contact. So if it is known that the reaction at contact is much faster than the arrival of the elements to each other, we can conclude that the factor limiting the reaction is the diffusion of the 2 elements, A and B. So this equation can be simplified even more if there are no Coulomb force between the elements. Then we get this Molchovsky equation for the diffusion-limited reaction constant for steady state. You can see it here. Yes, and for example, the reaction rate constant of 2 iodides becoming I2 molecule is 10 powered minus 15 cubic centimeter per second. Okay, so after we have calculated the necessary parameters, we simulated a basic solar cell containing electrodes, hole blocking layer, perovskite layer, and electron blocking layer, where there is a symmetry between the electrons and holes in the terms of energy barriers. We consider the properties of methylammonium lead triiodide perovskite to distinguish the effect of the ions on the reactions on the resistance of the blocking layers. We considered low charge carrier mobility in the blocking layers. And we chose diffusion coefficients for iodine species in the blocking layers to be 4 orders of magnitude lower than those in the perovskite. Afterward, we ran a time-dependent simulation where at t equal to 0, the device has no free ions and no illumination, and at t equal to 0 plus, the light turns on and the ions start moving and react in the layers. So we see here the course of the charges and the ions propagation in the device as a function of time. Yes, my cat, sorry. So the blue line is of ions, the purple of electrons, and the green is for holes. Here we can see the hole blocking layer, the perovskite, and the electron blocking layer. So the simulated time is noted here, but the real-time scale depends on the ion diffusion coefficient. And this is an example of a device where the ions can penetrate to the blocking layers and react with other elements. And also, if I will start it from the beginning, we can observe from this video that the more ions coming out of the perovskite, the blue graph, the more electrons enter it, the purple graph. So I will talk about it later. To monitor the effects of the ions and the reactions on the solar cells, we simulated 5 scenarios where the blocking layers are also ion blocking layers, with and without the reactions, when the ions can penetrate to the blocking layers, also with and without the reactions, and as a reference, a solar cell without ions. These are graphs of the charges and the iodine species distribution along the device close to the maximal power point voltage of the solar cells. So let's first look at the device without the ions, which is not a perovskite solar cell. We can see the charge distribution of a normal solar cell without the ion influence. Let's first look at the device without the let's first look on the 4 devices. So we can see that the presence of the ions cause approximately uniform charge distribution in the perovskite layer for all these graphs, which indicates the attenuation of the electric field in the layer due to the presence of the ions. And if we will compare each pair of the devices with and without the reactions, we will notice that with the reactions, there are fewer charge carriers, which indicates the combination process we talked about resulting from the reactions. And for the devices in which the ions emerge from the layers, there is effective n-type doping of the device. We can also detect a surface dipole between the layers. So here we have electrons, a negative charge, and here the lack of ions is actually positively charged vacancies. And another significant difference can be seen in the devices with the reactions. So the iodine species density is strongly dependent on the ion distribution and if they can or can't penetrate the blocking layers. Okay, so sorry. This is a JV characteristic of the 2 devices for which the blocking layers are also ion blocking layers, and the reference device without the ions, the pink one. So the measurements were made for forward and reverse scan, but because of the choice of the energy band structure, there is no hysteresis here. And it can be seen that with the presence of ion, the blue graph, the presence of ion decrease the serial resistance and increase the efficiency. But with the addition of the reactions that add recombination mechanisms, the efficiency of the device dramatically decreases. And this is the JV characteristic of the 2 devices for which the ions can penetrate the blocking layers, as well as the reference device without the ions. So these graphs were measured in the same conditions as the previous and with the same scanning rate. But here we can see that the hysteresis is prominent. So the ion distribution changes during the scan inside the blocking layers, and thus changes the current. As the ion penetrate the blocking layers also, the device efficiency, we can see here, decreases significantly. So we can explain it by these 2 graphs. Here we can see the charge and ion distribution in a device at 0.01 second, in which most of the iodides are still in the perovskite. And here at steady state, in which the iodides penetration to the blocking layers is more prominent. So when the ions leave the perovskite, electrons arrive to compensate for them. As the electron density increases, the recombination also increases, and the short circuit current decreases. We can also see this S shape here that didn't exist in the case in which the ion stayed in the perovskite layer, which means that the ion penetration to the blocking layers changes the charge extraction in the device. Yeah, and of course, with the reaction consideration, the device efficiency decreases even more. Okay, so in conclusions, the iodine species functions as recombination centers, thus lowering the efficiency of the device. When the iodide ions leave the perovskite layer, electrons enter it to compensate for them, so the recombination increases and the PCE decreases. This model can explain the solar cell's time-dependent internal degradation, even when it is encapsulated and not exposed to environmental conditions. But to make this model more accurate, we will need further experimental information regarding the reaction rates constant and which reactions are dominant. And this model doesn't consider secondary degradation phenomena caused by the ionic movement in the blocking layers and contacts. So it cannot accurately predict the degradation. Okay, so thank you very much for listening.